Okay, so we're looking at question 7. I'm going to try and get through some of these a bit faster. When two circuit elements are placed in series, we've got 4 options. The power produced by in both must be the same. Well, that's clearly not right because we're going to have a voltage drop across each, and therefore a voltage drop across each means we can have a different power which is produced. A current in both must be the same. Well, if it's in series, then that there you go. That's what it is. The current around a series circuit is the same. So if we start with here's our series circuit. Doesn't matter how many things you have in series. There's only one path for the current to flow. So that current is going to go around, and that current is going to be the same. Question 8. Consider the circuit shown below, yada, yada, yada. What is the total or effective resistance in the circuit? Well, it's a pretty straightforward one, but we have to also consider that the internal resistance of this cell, this battery, is 2 ohms. So the total resistance is just the sum of, because it's a series circuit, the sum of each of the resistances. So we've got 80 plus 10 plus 8, 90, 98. So that's going to be 100 ohms. Most students don't really have any problems with that. It's more just when they're doing parallel circuits, they have a bit of trouble. Determine the current in the circuit. Well, simple Ohm's law, that one. So for the current in the circuit, I is equal to V over R, which is equal to 100 volts divided by 100 ohms, which is going to give us 1 amp. Calculate the potential across R1, 2, and 3. So I guess this is where setting out is very important. First of all, we want V of 1 is actually going to be the current through 1 times the resistance of 1, which is equal to, well, the current we know to be 1 amp, and the resistance of 1 is 80 ohms. So there's going to be 80 volt drop across 1. For 2, no surprise, the voltage across 2 is the current across 2, which is the same for all of them, because it's a series circuit, times the resistance of 2. So there's going to be 10, 1 times 10 is 10 volts across there. So if we were to get a multimeter and we want to measure the voltage here, remember it's got to be in parallel, V1, then that would measure out to be 80 volts. So most of the volts, most of the voltage will be dropped across that first resistor there. And then, of course, this one is going to be 10 volts. The next one, as you can see, is going to be 8 volts. So V3 is going to be 8 volts. And there is a small voltage drop across the cell as well. That's going to be 2 volts. What is the terminal voltage of the battery? Well, that's going to be we've got a 100 volt supply, but there's an internal resistance inside the battery. So therefore, the terminal voltage is going to be the 100 take 2. So the terminal voltage, we'll call it V of T, is equal to 98 volts. Calculate the total power produced by the battery. Well, the power is equal to V times I. Now it's still outputting 100 volts, but so there's still going to be 100 volts with 1 amp. So we've got 100 watts of power. Okay, so let's have a look at question 9. When two circuit elements are placed in parallel, let's try and rule these out. The power produced in both must be the same. Well, that's not technically right, because if we have two resistors, we know that the voltage across the two resistors is going to be the same. We know that this voltage is going to be equivalent to this voltage. But we do know that the current going through here is going to vary, and on these resistances, R1 and R2. So given that the voltage and the current, well, the voltage is going to be the same, but the current's going to be different, clearly the power produced is not going to be the same. So by understanding those fundamentals, you can then, I guess, backtrack and cancel out all of these ones that don't sound too right. The current in both must be the same. Well, we just discussed why that's not true. The voltage across must be the same. So look, there you go, we've eliminated it. Look, you've got to recognise that fairly quickly. Question 10, and that is such an important point, that voltage across a parallel circuit. I'm going to just drum it over again and again. The voltage is the same, and the current is split. Now it's split depending on the resistances, and you can use Ohm's law to find those out. Three resistors in a circuit are connected in parallel with a battery, and it has a zero internal resistance. Most of them you just have your battery, and we're going to assume that there's no internal resistance. Calculate the total resistance of the circuit. So first of all, you can sort of, the equivalent resistance of a parallel circuit, I like to use this one. 1 over R1 plus 1 over R2 plus 1 over R3 to the negative 1. So we've got 1 over 100 plus 1 over 200 plus 1 over 600. The power of negative 1. Just pump that into your calculator. Make sure you're using the brackets correctly. And from there, I'm just going to work that out. From there, I've got an answer of 60 ohms. So that's going to be 60 ohms. Now, importantly, if you ever get a value greater than any of these resistors, 100, 200, or 600, you know you're wrong. It has to be less. So that's going to make sure that you understand that, so that way if you do an error in your calculations, you can go back and fix it. So that's the total resistance of the circuit. To determine the total current, well, if we have the total current, pretty straightforward. The current is the voltage divided by resistance, which is 120 divided by 60, so which is 2 amps. Calculate the branch currents. So this is obviously, yes, the voltage across each of these is going to be the same. There's going to be 120 volts across each of these resistors, but the current will split depending on the resistance. So let's have a look. I guess if we go and we use Ohm's law, so I1 is equal to V1 over R1. Now we know the voltage across all of them is going to be 120 volts. And resistance 1 is 100 ohms. So we've got 1.2 amps flowing through resistor 1. Why? We have a lot more. So considering we have over half the current flowing through resistor 1. Why? Because it has less resistance. So more current is going to flow through. Current chooses the path of least resistance. Doesn't mean all the current's going to go through there, but most of the current's going to go through there. If we were to work out I2, it's the same thing. It's equal to 120 over 200 which is equal to 12 divided by 2 is the same as 6 divided by 10, which is equal to 0.6 amps. And we know that we don't even have to work out what I3 is, because we know that the total current total current must be 2. So we've got I3 is going to be 0.2 amps. Determine the power output of the battery. So part D, power output is equal to V times I, which is 120 times 2, which is 240 watts. And finally, calculate the total power consumed by all the resistors in the circuit. Well, if you think about it, they're the only three components in the circuit. So all the power is going to be across all of those resistors. We've got a 120 volt drop from here to here. So the power drop across those resistors is also going to be 240 watts. So the answer to E is also 240 watts. All right, let's have a look at the next one. I know I'm flying through some of these, but I certainly don't want the videos to go for too long. Let's go ahead and do question number 10. There's a lot of reading here, so let me just work through it, because I'm looking at this the first time too. Belinda needs to operate a portable tape recorder requiring at 12 volts. I'm going to start underlining these. I'd suggest you do the same when you're doing these questions and write down what you know. She has some 1.5 volt dry cells, which each have an internal resistance of 0.3 ohms. Now she needs to require 12 volts. So how many of these is she going to need? 8 of those is going to give her, if she has 8 in series, 8 of these in series, that's going to give her 12 volts and so on. So, but each of those is going to have an internal resistance. 8 times 0.3 is equal to there's going to be 2.4 ohms of resistance in lining up those. And okay, so she has a 1.5 volt, and each have an internal resistance, and a small 9 volt battery with internal resistance of 5 ohms. So let's have a look at, or she could have a 9 volt battery that has a resistance of 5 ohms, which then means that she'd have to have 2 resistors. She'd then have to have 2 1.5 volts in series with that, which would then give 5.6 ohms of total resistance. Belinda decides to connect 2 of the dry cells in series with a 9 volt battery to provide an EMF of 12 volts. For a tape recorder, assume the batteries are all fresh. She measures the voltage of her new battery with a voltmeter to check whether it's satisfactory. What does she find? So, in this example, sorry, I just lost the screen there for a while, so you probably heard a whole lot of nothing. In this example, she has 12 volts. There's actually going to be, since it says here, it's operating at 100 milliamps, and there's this internal resistance inside the cell, and the total internal resistance is 5.6 ohms. So if we take away voltage, current, voltage equals current, which is 100 milliamps, 100 by 10 to the minus 3, times 5.6 ohms. If we work that out, it's going to be 12 minus 0.56. So she's actually going to get, when she measures it with the voltmeter, she's going to get approximately 11.4 volts. So she's going to, due to its internal resistance, she's going to have about 11.4 volts. She's going to measure across that. What problems do you see with Belinda's arrangement? Well, the 9-volt battery will go flat before the others. As it says there, 9-volt battery will go flat before the others. Why does it would go flat? Well, we worked out that if we were to have her arrangement of 8 cells, that was only a total resistance of 2.4 ohms, whereas the 9-volt battery and the 2 batteries in series had a total resistance of 5.6 ohms. So, yeah, that's so it'd be better for her to actually have the 8s connected in series. Next question, what's this one? No, so that one's done. The following information applies to question 14 to 17. What current flows through if a PD, or potential difference, 100 volts is applied to the element? So let's just track this up. Now this is it looks ohmic from sort of here to here, and then from there it doesn't have this linear relationship. So this certainly is non-ohmic. And this to me looks like an ohm relationship, Ohm's law. What currents? We're just tracking that through. So we should have for 14 is going to be 2 amps. What is the resistance of the element at 50 volts? Well, 50 volts is probably going to be, we can use Ohm's law for that. For 50 volts, we're going to be resistance equals voltage divided by current. So it's going to be 50 ohms. At 100 volts, same thing. At 150 volts, I'm just doing a bit of an estimate there. Let's say 2.7. So 150 volts, we're going to get, say, 150 divided by, say, 2.7, which is approximately equal to, say, 55 ohms. Just having a guess though, aren't we? And for 200 volts, the about 200 divided by 3, which is about 66 or so. What power we produced at 150 volts? At 150 volts, we worked out that was probably about 2.7 amps. So P is equal to 150 times, so just reading straight off the graph, nothing too strenuous here. About the 400 watt mark. You guys can check that though. What do you think that the resistance at 200 volts would be greater than 100? Why do you think that the resistance at 200 volts would be greater than 100 volts? Well, I guess with this one, what's happening as you're supplying, so more voltage was proportional to resistance, current, and what happens is that as the current is higher, there is more potential for charges, and what will happen is that the wire get hotter, and the increase in heat will increase resistance. The element's going to get hotter. That's about all I can really say for that one. Question 18. So I'm going to plow through some of these fairly quickly. Circuit shown 400 volts and internal resistance 2 ohms. Switch is closed initially. So let's have a look at this switch. This is the switch here. So if it's closed, we've got a path for electricity going to flow in this direction here from positive, conventional current from positive to negative, electron current's the other way, negative to positive. So positive to negative, it's going to come up this way, and we need to calculate the total resistance of the circuit. Well, the total resistance of the circuit, we have to also consider the internal resistance of 2 ohms. So 100 plus 80 plus 18 is 198 plus 2 is 200 ohms. So that's part A. Part B, determine the reading on the ammeter. Well, the ammeter's down here, and that's going to just be the total current for the system. So current is equal to voltage 400 divided by the total resistance, which is 200. So that's going to be 2 amps. Determine the reading on the voltmeters 1, 2, 3, and 4. Well, the voltage drop is going to be proportional to the resistance. So we know that of this 200 ohms, without even doing any calculations, we could automatically say that the voltage drop across that 100 ohm resistor is going to be half the voltage. So I'm going to just say V1 is equal to, and there's no problem with that. If the question is just asking for an answer, if you can work it out just like that because you know these principles, that's going to ensure you're going to do much better on exams next year if you know these principles rather than just plugging numbers into formulas. It'll only get you so far. V2 is going to be, well, if we think about 80 over 200 as a fraction, that's going to be the same as 40 over 100. So 40% of the voltage is going to go through this one here. So 40% of, well, 10% is 40%, 160. So there's going to be 160 volts across there. For across 3, well, let's actually use Ohm's law for this one. So V across 3 is equal to I across 3 cross with the resistance of 3. We know the current's 2 amps, so it's 2 times 18, which is equal to 36 volts. And since the total voltage drop across everything has to add to 400, we've got 160 plus 36 is 196. 196 plus 2 volts. So V of 4 is going to be 4 volts. Okay, so we've done this, and this. Determine the power produced by the battery. Power is voltage times current. So you see these questions are really starting to repeat themselves now, aren't they? Voltage times current. Our total voltage is 400. Current is 2 amps. So we've got 800 watts of power. Calculate the power consumed by the 3 resistors in the circuit. Well, the 3 resistors in the circuit, there's 196 volts across them. So the power across the resistors in the circuit is going to be 196 volts times our current of 2. Sorry, 396, Times 2, 6. So we've got 792 watts of power across these three resistors here, which is going to leave the final 8 watts of power is going to be across here. What is the terminal voltage of the battery? Yeah, that's 4 volts. Oh, sorry, the terminal voltage is the 400 take away this 4 volts, which is equal to 396 volts. So that's that done. And what is the terminal voltage of the battery if S is open? Well, if S is open, then there's not going to be then clearly there's not going to be a path for this to flow. So it's basically just going to be the voltage across the battery. Now, given that there's an internal resistance of 2 ohms, then if we have 400 volts, we have to take away the current. Well, there's not going to. Okay, so in this case of the terminal voltage, if the switch is open, the current is not clearly not going to flow through here. So all we could still measure a potential of 400 volts across the battery. So for part G is going to be 400 volts. However, you plug it into this circuit with 3 resistors in series, and you're going to have a terminal voltage of 396 due to the fact that the electricity is flowing through the resistors and constantly flowing through that that battery. Okay, so let's we're almost getting there. What have we got? Okay, a lot of these multiple choice now. Okay, special type of circuit, device X, is depicted in the graph. The circuit device X is connected in the circuit as shown, yada, yada, yada. How would you describe the device X and what is its purpose? Well, let's have a look at the graph. What you notice is that it gets to a current of 2 amps, 2 milliamps. And then no matter how much voltage is across it, the current is restricted to 2 milliamps. So there's a number of reasons why we might want that. Number one, we don't want the element to get too hot. So this is a voltage. This is your common. This device is used to restrict the current through the circuit. So how would you describe X and what is its purpose? What question is this? Question 20. Just trying to think of a better way to explain it. Well, I checked the book's answers, and it's basically exactly what I mentioned. First of all, it's non-ohmic, and it's used to reduce the current in the circuit. Part B, describe the resistance of such a device in the voltage range of 60 to 100. Well, from 60 to 100, the resistance is V equals 9 times. So it's going to be, like for example, at 60, it's going to be 60 divided by 0.002, which is, say, 12,000 ohms. Just having a look. But basically, as the device increases in voltage, the resistance is the voltage divided by the current. So as the voltage increases, the resistance increases as well. Determine the readings on voltmeter 1 and 2. Well, we have, so we know that for this part, we know that the current is equal to 2 milliamps, 2 by 10 to the negative 3. And we know that the voltage is equal to 250. So we can work out the total resistance is 250 divided by 2 by 10 to the minus 3. I don't have a calculator, so let's just do it this way. That's going to be 125 by 10 to the 3. So we're going to have a total resistance of 125 kilo ohms. So therefore, X is equal to, it's going to have to be 75 kilo ohms. Determine the readings then. Well, voltage across 1 is equal to the current across 1, which is 2 by 10 to the minus 3. Times the resistance, which is 75 by 10 to the 3. These two are just going to cancel each other out because it's going to be 10 to the power of 0, which is 1. So the voltage across 1 is going to be 150 volts. And, well, funnily enough, they're going to have to total to give 250. So we know that voltage across 2 is going to be 100 volts. How much power has been consumed by the circuit device X? Well, if you think about it as a fraction, let's have a think about it without doing any calculations. 150 of the 250 volts is going through 1. So let's have a look at, or the voltage drop is through 1. So 150 divided by 250 is the same as 15 over 25, which is the same as 3/5, which is the same as 60%. And 60% of the voltage, well, 10% of the voltage is 25 volts. So it's going to, well, 60% of the power is going to be go through 1. How much power is being consumed by the circuit device X? Well, power is equal to V times I, which is 150 times current, which is 2 by 10 to the minus 3. So we've got 300 by 10 to the minus 300 by 10 to the minus 3, which is 0.3 watts. So there's going to be 0.3 watts across here. And that's going to be 60% of the total power. So how much power is consumed by R? Well, we'll do the same thing. P equals V times I, which is 50. What did I do there? 150. Yeah, so we've worked out from before that 100 volts So we've got power here is equal to 100 volts times 100. I keep getting confused. 2 milliamps times 2 by 10 to the minus 3, which is 200 by 10 to the minus 3, or 0.2 watts. So as we said here, then there's a total of 0.5 watts. And 0.3, well, conveniently, as we worked out, 60% of that power goes through this. The 0.2 watts, or 40%, goes through 40%, goes through here. What is the power output of the 250 volt battery? God, you can work that out. Add them two together. It's not hard. The following information applies to 23 to 25. So this is actually looking at, we have supply cables, and we then transmit them across lines. There's going to be a resistance across these lines, and that resistance is going to eventuate the loss of power. What is the maximum current likely to be used by the household? Let's have a look. So at the time of maximum load, which is P power is 10 kilowatts, 10,000. Okay, so we have 10,000 watts, and the voltage supply is 240 volts. So the current at maximum, this supply here, is equal to 10,000 watts of power divided by 240. What's that? 10,000 divided by 250 is around about 42 amps, maybe. I don't know, it's too late. I might as well just check the answer. 42 amps, okay, I'm right. Okay, so we've got 42 amps of current at the maximum time. What will the voltage drop across the supply cables be? Well, look, voltage drop. So, under a minimum load. Okay, so under a minimum load, the power is equal to 120 watts. And 120 watts. Okay, so we've got, first of all, we have to consider that there's two lines. So each of these is going to have a resistance of 0.5 ohms. So the total resistance of the lines is going to be equal to 1 ohm. Now, if we've got the current, obviously, if we step down the voltage, we have the same voltage with less power, we have less current. So less current is good because obviously we have less power loss, because power which is lost is equal to I squared times R. So the power loss is equal to 0.5 times 0.5 is 0.25 times R, which is 1, so it's 0. So I'm going to lose 0.25 watts. Now, considering that we've got 0.5 amps. So how do we work out the voltage from here? Well, 0.25 I'm just going to stop there. I've had a bit of a lapse in memory. I'll stop there and I'll probably come back to that one. Light bulb rated at 6 watts, so we're going to push 30. What voltage is required to operate the light bulb correctly? Well, we know that the 0.5 amps goes through, so the current is equal to 0.5. And we know that the power must be 6 watts, otherwise it's not operating correctly. So therefore the voltage is equal to the power divided by the current, which is equal to 6 divided by 0.5, which is equal to 12 volts. How many volts will there be across a resistor when the circuit is operating correctly? Well, if there's 12 volts across here, then clearly we need 8 volts to be across here. So it's 8 volts. And what is the required resistance of R? Well, we need to know, if we've got 8 volts across there, and we know that the current going through here is 0.5, so we know what the current is. So resistance is voltage divided by current. Now we know that 8 volts goes through there, and we know the current is 0.5 amps. So that's going to be 16 ohms. So, well, we could work out even what this is. If we know that 12 volts goes across there, we know that the resistance of this section here has to be greater than 16 ohms. It actually has to be half. Obviously, the ratio between 8 and 12 is that 12 is 1.5 times greater than 8. So you could actually work that out, 24. So we could actually work out that the resistance across here would be 24 ohms. Probably not even asked to do that anyway. And look, I'm going to stop there. That's plenty. That's well and truly an hour's worth. I hope that this is helping you with your SAC preparation. In summary, though, the main formulas that you'll need to know is obviously power equals voltage times current. If I was to go back up here and have a look at some of these questions, you clearly need to know that working out the power at different areas of the circuit, you need to know that, or read from a graph, that read voltage and current from a graph and then use them in your calculations. Need to work out the voltage drop across different components in a circuit. You also will need to, you may need to connect or consider that cells can be connected in series to form a total voltage. As you can see, though, that a lot of these questions revolve around circuit theory, and so in particular, I think the most important part for you to realise is how voltage and current splits around a circuit. Voltage in for volts. In a series circuit, there's going to be a voltage drop across each component. For current, the current's going to be the same in the series. In the series connection, For parallel, the current's going to split, whereas the voltage drop is going to be the same. And you can use Ohm's law to calculate voltage and current throughout. And of course, you can work out resistances as well. So I'm going to leave it there, and yeah, good luck for your studies.